Many may know Isaac Newton for his brilliant discovery made due to the falling of an apple. However, he is known for much more. Sir Isaac Newton was an English physicist who is widely recognized as one of the most influential scientists in history. He has established many laws which have led to many scientific advances throughout history. Today, Kayla and I will be addressing Newton's 3 laws of motion and be demonstrating how the laws apply to daily life. Newton's first law, also known as the law of inertia.
Oh, you caught me off guard there. I was just having a pretty weird dream, actually. It was a pretty cool concept, and I want to see if it works out. Come on over, let's check it out. I'm going to be honest with you. My dream was actually about Newton's first law. It's the law of inertia. It states that an object in motion will stay in motion, and an object in rest will stay at rest, unless it's acted upon by an unbalanced external force. So I was thinking about a way to test it out. Look at this. Perfect. We have a glass of water. We have a plate. We have a toilet paper roll. And we have an egg. Objects with more mass carry more inertia, which means the more of a tendency to resist motion. So this egg has more inertia than this paper towel roll. Alright? So according to the law, if I apply no external force on this egg, it should be not moving, right? But an egg isn't going to stay floating in the air. So the only force acting upon it should be gravity, which means that if I position it just perfectly, it should fall directly into the cup. Newton's first law. My demonstration was with a cup filled with water, a plate on top of that, a paper towel roll, and an egg. My applied force was a forceful one, just to the plate. There was no external or applied force to the paper towel roll or the egg. After I applied my force, the plate moved out of the way with the paper towel roll, leaving the egg still in the air for just a moment before it fell straight into the cup. This is because the egg has more inertia than the paper towel roll. More inertia is the more of a tendency to resist motion. This is the free body diagram of the egg. As I said, there was no external or applied forces to unbalance the net force of the egg. The egg had more mass, meaning more inertia, and it did not want to move or change its motion, which is why it fell straight down into the cup, meaning for one lucky egg.
Newton's first law states that if the net external force of an object is 0, the object will remain at rest or continue to move at a constant velocity. As you can see here, the billiard is at rest and will remain at rest unless acted upon by an external force. When I strike the ball with the cue stick, the billiard continues at a constant velocity forward. If there were no external forces acting on the billiard, it will continue at the same velocity without stopping, forever. Now, because of forces such as gravity, air resistance, and friction from the felt, the ball is forced to come to rest. All these forces cause for the ball to accelerate negatively, coming to a stop. Here is a free body diagram for the ball when it is motion. As you can see, there are 4 forces acting upon the ball. There is a normal force, the force of gravity, the force applied, and also the force of kinetic friction, which ultimately causes the ball to come to rest. Newton's second law.
Wow, what a great day out. Forget that though, let's talk about something more important. Newton's second law. According to Newton's second law, force is equal to the product of an object's mass times its acceleration. This means that the force of the object should be directly proportional to its mass. Am I right? With constant acceleration, of course. So, if we were to try this out, we would need objects with completely different masses and somehow get to the exact same acceleration and see how that affects its force. Oh, look at this! Perfect. Let's go try it out. Okay, so we found objects with 2 completely different masses, this one being greater, of course. So we found out that According to Newton's second law, if the object's mass is greater, the force should be greater on impact with a constant acceleration. So here we have a constant acceleration of 9.81 meters per second squared. So these should hit the floor at the exact same time, no matter what the mass. Let's test it out. So according to the law, the force of impact of the greater mass object is much greater than the one with less mass, and you can see that by the indents in the sand. As I stated earlier, Newton's second law states that the force of an object is equal to its mass times its acceleration. This means you can rearrange this equation to solve for things such as acceleration and mass. In this case, force divided by mass would be acceleration. Newton's second law also states that mass is inversely proportional to acceleration with a constant force, and that mass, in this case of my demonstration, was directly proportional to force with a constant acceleration. To talk about my demonstration, I'm not sure of the exact mass, I just knew that one was more than the other, so in this case I'm just going to use 10 and 5 grams of mass for each of my objects. The force is equal to the mass times the acceleration, and as I drop them from the same height, they hit the ground at the exact same time because of the acceleration of negative 9.81 meters per second squared, which is the acceleration of gravity. My demonstration clearly showed one of the components of Newton's second law. As you increase the mass, the force is also increased with a constant acceleration because they are directly proportional. I could see that by the indents in the sand as they got greater. This is the free body diagram of both of my objects. They both have only the force of gravity and the force of normal affecting them. Since these two objects were released from the air at the same time at the same height, the only two forces acting upon them and that are present in the free body diagrams are the force of gravity and the force of normal.
Newton's second law states that if the net external force of an object is not zero, the object will accelerate in the direction of this net force. The magnitude of the acceleration is directly proportional to the magnitude of the net force and inversely proportional to the mass of the object. It explains the formula force equals mass times acceleration. If there was a giant rock blocking a road and a little boy tried to move it, the rock would only move slightly. However, if someone older and stronger were to move the rock, it would move a much greater distance. The little boy applies less force, therefore there is less acceleration, and the older boy applies a greater force, therefore there is a greater acceleration. This reinforces that the force is proportional to acceleration. Now, if the rock was 10 kilograms and the little boy applied a force of 2 newtons, the acceleration would be only 0.2 meters per second squared. And if the older boy applied a force of 5 newtons, the acceleration would be 0.5 meters per second squared. Thus, there was a greater acceleration when the older boy pushes the rock compared to when the little boy pushes the rock. When drawing the free body diagram for this scenario, we're going to assume that there is no friction. So there are 3 different forces that are being acted upon the rock. There's the force of the normal, pushing the rock upwards, and there's the force of gravity, which is pulling the rock towards the center of Earth's core. Now, when either of the boys push the rock, there is also an applied force. Newton's third law. Newton's third law states that for every action, there is an opposite and equal reaction. Consider driving a bike into a wall. The bike imparts an action force on the wall from its motion, and the wall imparts a reaction force back on the bike, causing the bike to stop. These vectors are equal in length and point in opposite directions. For the free body diagram of the bike, there are 4 forces. We have the force of gravity, we have the normal force, we have the applied force of when you're riding the bike, and then we also have the force of the wall, which is an opposite of the direction of the applied force that we're placing on the bike when we ride it. So this is what causes the bike to come to a rest. Now in this scenario, we're assuming that there is no friction. Now here's another example. When someone is standing, there are two equal forces acting upon them, allowing them to stand still. There is the force of gravity, pulling the person downward towards Earth's core, and there is also the normal force pulling the person upwards. Once again, both these vectors are equal in length and in opposite directions.